Welcome to lesson 5.3, Satellites and Celestial Bodies in Circular Motion. First of all, what we're going to start off with is just realizing that while often we make the assumption that satellite orbits are circular, they are not in fact circular. They are in fact a lot more elliptical than we like to believe. So elliptical is kind of like an oval shape, and a lot of times we assume circular, but they are in fact oval. Now, this was discovered by Johannes Kepler, and now he used somebody else's data to describe the motion of the planets. And one of the big things here, first of all, is that the planet's orbits are in fact ellipses with the sun out of focus, right? And there are these imaginary lines sweeping through equal areas over equal time intervals. So what does that mean? Well, if we take a look at this little animation here, the satellite here is moving around the planet. It is moving slowest when it's furthest away. It is moving fastest when it is closest. However, during equal times, when it's close to the object that it's orbiting, the celestial body it's orbiting, it's going to be a short, wide, triangular shape, where when it's farthest away, it's going to be a skinny, long portion. Now, this is actually quite pronounced. Most satellites are not quite this pronounced, but just kind of gives you an idea. There is one equation that is very important as you're coming through this. That's this one here. Okay? And this is known as Kepler's equation. Now, you're going to get this anytime this comes up. It's not on the formula sheet, but it's basically the period squared divided by r cubed. Now, any ratio of any orbiting body will get you Kepler's constant, and you can compare that with any other orbiting body. So we can call this body A, we can call this body B. But as I mentioned, we're going to give you this formula every time a problem comes up with this equation. So a couple of definitions for you. The first one is the astronomical unit. An astronomical unit is the average distance from the Earth. To the sun. Now, again, we say average, but that's because, again, it's oval. It's that elliptical shape, and so it's not always going to be the same. Now, the number here is 1.5 times 10 to the positive 11 meters. And eccentricity is the variation of an orbital path. So in essence, I'm going to make up a word here. It is the ovalness of the path. So if, for example, we were to take a look, this path has less eccentricity than, let's say, this path. The more oblong the shape, the more eccentricity that path will have. So let's take a look at an example here using Kepler's equation. So in this case, celestial body sits 5 astronomical units away from the sun. What's its orbital radius? Well, that's a very poorly worded question. We should actually change that to period. Okay, so we're going to change that to period. Because otherwise the answer would just be 5.5. Okay, so t squared over r cubed is equal to t squared over r cubed. And you're probably wondering now, well, we've only got one number here, this 5.5 radius of the celestial body, and so we would go t squared of this body divided by 5.5. What do we compare this to? Well, probably the easiest one to compare to would be Earth, because the period of Earth is 1 year. And the average distance of the body is 1 astronomical unit. And so really you're left with a t squared over 5.5 cubed, put my cubed in there, is equal to just 1. Or t squared is equal to 5.5 cubed. So to find the time, you're going to square root that. And so the period that you wind up with here is, in fact, 13 years. Now, I should emphasize that that is Earth years, not the planet years, because the planet year is just defined as the distance it takes for the object to move around the sun. Okay, let's take a look at this next example here. So in this case here, the moon has an orbital radius of 3.8 times 10 to the 8 and rotates around the Earth every 27.5 days. How far from the Earth would a satellite rotate around the Earth twice a day? So t squared over r cubed is equal to t squared over r cubed again. Now in this case, first of all, we're given the period of the moon, 27.5 days, and so we'll square that. And the distance, it is the average distance anyway, is 3.8 times 10 to the 8, and we're going to cube that. And that's going to be equal to, well, the period of the satellite is half a day, right? If it's going twice a day, then half a day would be there. And you're actually looking for r cubed. So we're going to need to manipulate this around a little bit. 0.5 squared. And we're going to multiply that by the 3.8 times 10 to the 8 all cubed. Divide that by the 27.5 all squared. So calculating that, your r cubed is 1.81 times 10 to the 22nd, and after you cube root that, you wind up with 2.6 times 10 to the 7 meters. But that is its orbital radius. We do not want the orbital radius. We want to know how far from the Earth. So we're going to have to subtract the radius of the Earth here. Subtract the 6.37 times 10 to the 6 meters in order to get your final answer of 1.99 times 10 to the 7 meters away. Okay, give this next one a try. How long is a year on Mars? And pause the video and we'll come back to it. So what you should find here is that you wound up with t squared over r cubed. Compare it to Earth. Radius you've been given is 1.5 astronomical units, and you should have wound up with 1.8 Earth years as your period. So moving on, Newton's law of gravitation, he suggested that if a cannon was fired so fast that as it was moving, it would fall, and if the amount that it was moving away from the Earth equaled the amount that it was falling to the Earth, it would in fact orbit, or is basically escaping gravity. It's not actually escaping the gravity, it's just falling in pace with the amount that it's leaving. And he calculated that to be 4.9 meters for every 8 kilometers traveled. And that would match the arc. And so what we have is the centripetal force is equal to the gravitational force. We can see this happen several times, and we're essentially making the formula as we go. The escape velocity here. So in this case, centripetal force mv squared over r. Now that would be the mass of the cannonball. And that is important because when we take a look at our formulas here, what we see is the mass of the cannonball and mass of the cannonball cancel out. We don't need to worry about them. R, one of the r's will cancel out, and so you're left with v squared is equal to gm over r, or the velocity would be square root of gm over r, where m is the mass of the Earth and r is the radius of the Earth, because that would be the orbital radius of that cannonball. So we're going to plug in our numbers. 6.67 times 10 to the negative 11. Mass of the Earth, 5.98 times 10 to the 24, all over 6.37 times 10 to the 6 meters. And you wind up with a velocity of 7,913 meters per second. I know that's 4 digits and the question went a little beyond, but we'll work with it. Well, what happens if this satellite was 100,000 meters above the Earth? Well, the basic principle of what we did above still applies, and we get ourselves to this point. It's just that the radius now, G and M are the same, is going to be 6.47 times 10 to the 6, because we now got a higher radius, and because we got a higher radius, we don't need to move as fast, and we wind up with 7,852 meters per second. So here we're taking a look at a geosynchronous satellite. Geosynchronous satellites will orbit every 24 hours. So the planet's here, the satellite's taking 24 hours. 24 hours to circle the Earth. So its period is going to be 86,400 seconds. And we're going to use this because we don't know the speed of the Earth, but what we can do is use m for pi squared r over t squared is equal to gmm over r squared. And we're looking for the radius. The mass of the satellite cancels out, which is handy because we do not have that. And as we isolate r, we get r cubed is equal to gmt squared all over 4 pi squared. So again, r cubed, we're going to plug in our numbers. 6.67 times 10 to the negative 11, 5.98 times 10 to the 24, 86,400 squared, all divided by 4 pi squared. So r cubed is going to be 7.5 times 10 to the 22. Cube rooting that, r is 4.225 times 10 to the 7 meters. But we want to know the height of it, so we got to subtract the height of the Earth in order to get the final answer of 3.95 times 10 to the 7 meters. Give the last one a try, and you should have found 1,008.